So let's draw a diagram to visualize the situation that we have. So we have a square wire of side A, and then it's at a distance of A from both sides of the outer wire. And then we're told there's a current that's going in a clockwise direction, and then this current is increasing at a rate of k. So we want to find the EMF that's being induced in the outer wire. So how do we do that? So the first thing to do, of course, is that we consider the flux going through the outer wire, so going through the surface that's being enclosed by the outer wire. But then you'll see that the flux is actually really difficult to calculate. So this square loop hoop here generates a magnetic field, and then you know that it's going to look really weird across this region. So it's really not very practical to calculate it directly. But the fortunate thing is that inductance works both ways. So the amount of flux that's going through this giant hoop because of this square hoop over here is going to be equal to the amount of flux that's going to go through this small hoop if the magnetic field is being generated by this outer wire here. And then in this case, it's easy to calculate because for this long wire here, we know how to calculate the magnetic field. So it's easy for us to find the magnetic field going through this small hoop because of this outer wire rather than the other way around. So the other way around is calculating the flux through the region enclosed by this large wire because of the small hoop. So this is difficult to calculate. So we're going to adopt the easy way to calculate the flux, and that's to do it the other way around. So first of all, let us try to find the flux. So if there's let's say there's a current going down here, so there's going to be a magnetic field that's going to be equal to something like this. So S is going to be a distance away from this wire here. So this is going to be a magnetic field, and the same contribution is going to happen in both ways. So if it's coming down, then it's going to go back up, and then you'll see that either way the magnetic fields from both of these wires are going to point in the same direction. So I'm going to calculate it for one side and then multiply by 2 to incorporate the two wires. So let's focus on one wire first. So we have one wire going down. The amount of flux that is going to pass through this tiny square over here is equal to the magnetic field. So for dA, I'm just going to take away one dimension. I'll just multiply it by A. The second dimension goes in this direction. That will be in terms of S, so ds. And then since I've taken away one direction, so one dimension, I can strip this down to just one integral. And then the bounds are going to go from A to 2A. So like from here to here. And integrating this is simple enough. So I have natural log of S, 2A divided by A. And then once you evaluate this, you'll find that this is equal to natural log of 2. So this is the amount of flux that is going through this region because of this wire. And then we know, thanks to the nature of how inductance works, is that if we reverse the roles, if we're trying to find the flux that is contributed by this wire on this larger hoop, it's going to be equal to this expression here. So the amount of flux that we're looking for is exactly what we have over here. So divided by, we're going to multiply this by 2 because there are contributions from both sides. So the 2 in the denominator goes away. So this is our flux. So in order to find the EMF, we're going to differentiate this with respect to t. And then, as you know, all these are constants. So all we have is a di dt, and that's just going to be equal to k. So there we have it. This is the magnitude of the EMF that's being generated in this larger wire due to the increasing current in the smaller wire here. So this is the answer. So the second thing that we want to find, so this is the magnitude. So the second thing that we want to find is the direction. So which way is the EMF pushing the charge towards? So as you can see, inside the small loop here, the current is going in this direction. And then as you can tell that there is going to be a flux that's going to point inside the page. And so by Lenz's law, nature is going to try to reverse that, and then the EMF that's going to be induced on the outer wire is going to cause a current that's going to create a magnetic field to counteract that increase of flux pointing into the page. And then if you use your right-hand rule, you see that, contrary to the arrows I've drawn, the the current is going to go in this direction, in the anti-clockwise direction. So for the direction, the answer is anti-clockwise.